Yeah. Dude, I'm telling you, I can't do this. My pride is gonna be right here. Read that. You got a left on a 5 and 5. Oh, I got a 4 and a half. I didn't take one. I think my brother is thinking on the floor. Huh? Yeah, I put up AP scholar with the same thing. It didn't really mean. Yeah, I put it on my wrist. It's so. That's really. Like a problem. Yeah. I think I'm really lucky. Yeah, I really want the AP score higher, but I don't really matter to this. Other ones get. That's cool. I already sent my coach. That's why I've been. You get your cat lab. Nope. I mean, yeah. I mean, it'll be good. It's like chemistry guys. He's the oversight of verifying. So then somebody who's glad, I used to be your last week. Play. Like it's had a big lab there. Oh, like yeah, I did like view. Then I'm thinking like the getting. And all those, I was like 5 to 8:30. I'm doing all the. You do the Saturday week, yeah. Saturday 8 a.m. I got work. I want to play. Mango's not right there. I can't. Mango's I someone together. I don't like. I think it's so much. I just never like class. Actually, you just taught us the trick. Also, yeah. Oh, you see things about it. Yeah. It's not pretty good. I think it was a very good price. The price is second. Is that or take the lane exam again? I didn't myself too. Well, I was a living kind of lucky. Like, I mean, to take it, yeah. Oh, wait. I think I'm like. So it's like my lap. Holy crap. Freaking word.
So on the forward section, the summary of equations then memorize for chapter 11. So feel free to screenshot this.
Yeah. It's like It's how I type most of the time, but I was finding 15. Yes. Great. Yeah. So you can look at that and then right like when I was being trained and then break a lot of stuff. So you see, I think technology like you put out a openable phone, and then you put you still have the dual screen lap. So I don't know who screen it. I barely use the second because that's not like bring up. Yeah. That's so. No, I used to read this, yeah, that's why I use 16. Are you going to dunk this in something? Yes, I know. I'm actually can't have two things. I'm actually still in this chat. I actually automatically use everything right now. Yeah.
All right, so let's get started. Okay, so any questions before I go into the content of today? So everybody's actually holding up well enough. Okay, so we're entering we're almost finished the third week of this semester, right? And there's actually another football game coming up this weekend. I know everybody's going to be very busy, but make sure that you stay on track. Okay, so do your homework, do your quiz in time. Okay, and if you need help, reaching out to me as early as possible. Okay, so on the board is actually the equation I summarized for you. Those are the equations that you need to memorize for chapter 11. Okay. What we are going to go through today we're going to finish this chapter today, chapter 11 today, and the main thing they will need to learn is actually not much. There's actually two things we need to learn today. First is that we're going to learn how the scientists decide the law. When we propose, when we do the experiment, we use the experimental data to derive the differential rate law. Right? We do a lot of practice in the previous lecture. And what we're going to do today is actually, okay, if we do all these rate laws, then we eventually derive our differential rate law. Then we start to actually understand how this was happening at the molecular level. Okay, so we want to understand these things occur, how it occurs step by step. Okay, therefore, the scientists bring up this new concept. Okay, I want to write out a story. Okay, and this story was composed of multiple, we so-called elementary steps. Okay, and then using the concept of linking steps, okay, I can write out a powerful multiple step equations that eventually can explain the things I see experimentally. Okay, there are a few tips that we need to actually follow. Few rules that scientists actually create by their own. That's the best way to figure out the reaction mechanism. Okay, so we're going to learn that today. Okay, and the second thing is actually observing that many reaction kinetics. Okay, so scientists come with something called the activation energy. Okay, so the activation energy was actually evolved from the concept of rate limiting step. Okay, so when you actually complete one thing, there's always a big hurdles that we actually decide to make it or not. Okay, so that hurdle is actually the metaphor of activation energy. So we are going to introduce you the things you see, I guess you see for a long time from your chemistry courses in the past, when you are in high school. Okay, so we're going to find the energy of the reaction versus the reaction coordinate. Well, yeah, okay, I always problem with what is reaction coordinate, right? Everybody have good understanding what reaction coordinate means. So reaction coordinate essentially always starts from your reactant. It ends with your product, right? So going from your reactant to product, actually a few species you need to actually go through. Okay, so that process going from the reactant all the way to product, for other intermediate, for other transition states, you need to go through, right? And that is actually what scientists means or chemists means by reaction coordinates. Okay, so it is actually a time course. You start with the reactant, you end with the product. Okay, whatever you are in between, could be your intermediate, could be your transition state. Okay, so that's what it means. Okay, so I'm just going to create a figure like your y-axis is so-called the energy. Okay, a more term you can create is actually the delta H. Okay, or entropy. Entropy. Okay, so those are things you can plot on your y-axis, and the x-axis is actually your European coordinate. You also see how this species is going to transit, how the energy of this species is going to change along the way. Then we're going to actually tell you how to predict a reaction is exothermic and endothermic, right? And how to actually calculate the activation energy. How many transition state or intermediate you're going to have along this direction process. Okay, so those are the things that we're going to go through. Okay, and eventually we also want to actually provide you with the summary equation, which is actually the activation energy, how it actually relates to reactant rate constant K. Okay, so those are the very important equations I write. I actually move it on. Okay, so those are the equations that we will need to actually get really familiar with. And after that, after we understand all this concept, we are going to practice this concept with final questions for end today's lectures. All right, so let's start playing for today. Any questions? No? Okay, cool.
So before I actually go into all these things, let's do some practice. Can you think we haven't done these things for a while. Okay, so
It's kind of like we want to refresh our memory. Okay, the things that we do, we discussed this, right? The unit of K in the previous lecture. Okay, so trying to answer this. Okay, so the reason I want to pay attention to the unit of K is because from the unit of K, you can actually know the reaction orders. So, which is actually very important for the integrated level. Okay, any questions on this question?
Okay, so I'm going to bring this back so we can see this. So we went through this previously, right? The unit of K. We go through this one in the previous lectures. Okay, so the unit of K can be actually simplified into these general equations, right? So if zeroth order is n equals to 0, your K is going to have a unit of 1. 1 minus 0 as -1. That's actually just this, right? Molarity per second. So every time I write this, do you have questions? Is everybody familiar with this? Or everybody good with it? Okay. So n equals to 1, then your K is going to equal to what? 1 minus 1 per second, right? And that's this per second. So you have per second as unit for the first order, right? If n equals to 2, then you're going to have 1 minus 2 per second. That's n -1 as -1. Less per molarity per second. Okay. So for the zeroth order, that's what I'm going to have first order and second order, right? So first order is what? Per second, right? So it has to be BOC. And then it's zeroth order. Zeroth order is actually molarity per second, right? Oh, I have a typo here. So it should be M as -1, not -2. Okay, I'm sorry, I make a mistake here. So this one should be -1. Okay, so for the second order will be per molarity per second, right? So the answer should be B. Okay, so I make a mistake here. Okay, but in the end, it's actually important to memorize that general equation form. Okay, so you can do a quick check on your own. Then you will know if you see a rectangular unit, you will know what the direction order is. Okay. And that is important because once you know the direction orders, you know what integrated law you should use. Okay, so that's the first questions I want to go through. Okay, so this actually is second. For a single component chemical reaction, A change to B, bulk quantity changes linearly with time. For the zero, first, and second order reaction. Very good. I think everybody get the idea. So there's a three equation that actually to memorize, right? So for the zeroth order, you memorize AT equal to negative KT plus A0, right? So AT is actually the one. It's actually Y equals to X plus B, right? So Y is actually the term is going to depend linearly. Okay, so for the first order is actually natural log AT. equals to negative kt plus natural A0. And then for the second order will be 1 over AT, right? So the answer is actually C. Okay, so great. Everybody actually understand that. That's wonderful. Okay, so those are the things that I want to actually quickly went through so that I can make sure that you understand the content on Tuesday's lecture. Then we can go back to, oh, that's actually one more thing. Sorry. One more thing I want to actually tell you because I feel like I forgot to mention it previous. So go back to the integrated law. Okay, so these are the three equations we just talked about. AT, natural log AT, and 1 over AT, right? In your homework, you may encounter things called the half-life time, or T half. Okay, so what does that mean is that every time you see the T half, the really useful information to you is that the concentration at that time T is going to equal to the half of your original concentration. Okay, that's what it means. T half means your AT equals to half of your A0. Okay, so once you know that, you can actually rewrite the three equations. Then it will become 1 half of A0 equals to negative KT plus A0. Okay, so that's actually what you can get for the 0th order. Okay, then you can actually rearrange this one. So this T now becomes T half, right? So you can actually solve your T half is going to equals to, you move this whole term to the left first, move this one to the right. You will be A0 minus 1 half of A0. Therefore, you got A0 over 2 on the right. Okay. Then I divide the K on both sides so that I can get my T half will be this. Okay. So this means this is 2K, not 2P. Okay, so if the question tells you it's 0th order reaction, okay, if you give you the K, then you will be able to calculate the T half. Okay, using this simple concept. Okay. The other way that typically this information will be used is that if you give you the T half, okay, so I want to go back to this. If like question give you T half, that means actually you can calculate your K. Using this relationship. Okay, so sometimes the question won't give you the K directly. Instead, it gives you T half. Okay, so you need to actually know, once you know your T half, you should be able to actually figure out your K. Okay, so those are the little things that you might find useful when you do your homework or quiz. Okay, but we'll do more practice in week 5 when we actually do the reviews. I think we'll have more questions over there. Then this information will become useful. Okay, and you can see the same concept can be applied to the first order and second order. Right, so I would actually memorize this equation because once you know T half is actually your AT equals to half of your A0. You just plug that into the equation, then you can figure out the K very easily. Okay. All right, so those are the things that I want to cover before we actually head into today's lecture. Okay, any questions so far? Okay, then we're going to go to this reaction mechanism. Okay, so there are a few steps you need to actually follow. So you can answer the question properly. Okay. Every time you see this reaction mechanism type of questions, okay, the key information that you will need to actually determine or looking for is what are the elementary steps, okay, and among the elementary steps, what are the rate limiting steps? Okay, so those are the things that you want to have in mind. Okay, so once you can identify those things, have an idea, okay, what are your reactants? What are your products? What are your intermediate? Okay, sometimes you may be able to identify something called catalyst in the elementary steps. Okay, so first thing is actually to identify what you have. Okay, every time we write out the red laws, okay, we have a clear idea that the red law is based on only on the reactant. Right. So in your red laws, you never actually write out the concentration of the product. Okay, so that is actually a very important concept that you should have. Okay. That's why in the first step, okay, what you need to do is actually to decide, okay, what are your reactions. Okay. And then once you actually finish that, okay, the next concept that you should have is that if you have elementary steps, okay, you can actually write the red law directly based on the equation you write over there. And this is only true when you have elementary step. Okay, so when something is called this is elementary step, okay, it is literally, let imagine the reaction happen as a result. There's actually no further underlying processes going on. Okay, so elementary step is very, very special. It is not a regular equation that you see. Okay, it is the equation and only equation that you can write out this red law purely based on the layout of the equation. Okay, so you try to have a clear distinction between the elementary step from the normal chemical reaction equation that you see. Okay. And the third one is that the final red law will be determined by the relative step. Okay, let me say, when you're trying to write out the red laws from the elementary step, you need to starting from the relative step. Okay, so if you start from the non-relative step, and after all this process we're going to go through, you won't be able to get the correct result. Okay, and that's actually the way how scientists figure out what is actually occurring below. They just randomly try. Okay, they say, if I propose a reaction have 5 elementary steps, but I don't know which is actually a correct element, which is actually a relating step, right? So I start from 1. Then I start to actually substitute the non-reactants, okay, and see whether I can actually eventually get a red law that can match the experimentally determined one. Okay, but if I cannot, then let me actually I pick the wrong one. I go to the other step, consider that as relative step, and then repeat the process again until that the relevant I derive is consistent with the experiment. Okay, so we're going to do that practice today. Okay. And the way let's substitute the non-reactants is that we're going to use KEQ, the equilibrium constant. Okay, so I assume everybody has some sense about how to write the KEQ, right? So let's do some practice. Let's say you have a chemical reaction. Okay, 1A plus 2B plus 3C, that give you 4D plus 5E. Okay, so we know the equilibrium constant KEQ can be written as what? What's going to show on your numerator? Concentration of your product, right? So here the product is your D to the fourth power E to the fifth power. Denominator is actually the concentration of your reactant, right? Raised to the power to the coefficient, right? So A to the first power, B to the second power, C to the third power. Okay, so this will be the things that we're going to use a lot when we try to derive the final rate law from the deriving step. Okay, so make sure you know how to write your KEQ. Okay, any questions so far? All good? Okay. So let's look at some examples so you know. Another thing I want to say is, no, I guess I said everything. Let's look at this. Okay. So it says, consider the reaction A plus B plus C that give you D. Which is found to be first order in A and second order in B for their rate laws. Okay. Which step of the proposed mechanism below must be slow in order to agree with the rate law? Okay. So what is actually the overall chemical reaction we are going to deal with? Read the question. I haven't actually gone to the elementary step, right? I want to read the questions. So what is the actual chemical reaction we're doing? It's A plus B plus C that give you D. Okay, so that is actually the final chemical reactions that what you're talking about. Okay, and then in this question, it provides you this step 1, 2, and 3, right? Let's step 1, 2, and 3 is so-called the elementary step. Okay, and one very important thing that you should know is that when you add up the elementary steps, it should go back to the overall chemical reaction. Okay, so if you do these things very quickly, okay, if you just add the 3 step up, okay, so this will cancel out with that, right? This will cancel out with this. So that you know, if you add all these 3 steps up, you got this. Okay, so that means when you do a real experiment, all you can observe is what? A, B, C, and D, right? But to propose the elementary step, scientists have to actually add some new stuff. Okay, and those are species we call either intermediate. These actually things we call intermediate. Okay, so I want you to actually pay attention to this. Why do I call these things as intermediate? They say these are the real correct proposed mechanism. Okay. In the first step, you see your A is your reactant, right? B is your reactant 2. How X? Yeah, it's something new not created by when you mix A and B, right? But that thing is never be detected, okay, experimentally. Okay, but let's suppose that let's believe if you put A and B together, you first will actually produce something called X. And we call that X as intermediate. Okay, it's a very important concept. Okay, and then later on, that X that actually work with your steam to produce a species called Y. Okay, so Y is another intermediate. Okay, and then this Y eventually do some conversion and produce your final product B. Okay, So in this three-step elementary step, you can see you have two intermediates, okay, was proposed to connect every single process along the way. Okay, so then the scientists, after they proposed this mechanism, okay, now let's start to need to the other thing that you decide is actually which one is the rate limiting step. Okay, it can be 1, it can be 2, it can be 3, but only one of them will be correct. Right? How do I figure out the correct one? Is like the first thing to know what is the experimentally determined red law. Okay, so that's why I want to actually come back to this. Every time you see your hello, you can hear me? Okay, good. Every time we see this overall chemical reaction, you should know that the red law can be written as a rate constant K times your reactants, right? So you have reactant A, reactant B, reactant C to certain power, right? And that power is not the coefficient of your reaction. Okay, that power need to be determined experimentally, like what we did in the previous lecture. Okay, but here the question tells you the red law has found to be first order in A, first order in B, right? So those are the information you can write. It's first order in A, first order in B, right? First order in C. Does it say anything? Okay. If it says nothing means okay, very important. Okay, if it only says it's first order in A, first order in B, it doesn't talk about C, then C is actually zeroth order, less than default. Those are things that you need to account. Okay? That means the experimental determinant level will be what? The rate is going to equal to rate constant K times A to the first power and B to the first power. Okay. So now actually come to the end that we can calculate. Okay. So among the three steps, which one will be actually your rate limiting step? Okay. Okay, so so far I guess everybody's actually understand the things that I want to see. Okay. Now we come back and do our Q impact. Okay. So Q, what are the things that we want to figure out? So we want to figure out what are the rate limiting step, right? Rate limiting elementary step. Right, that's the things that you want to find out. You have three choices, 1, 2, and 3, right? Step 1, step 2, or step 3. Okay. And then so far the things that we know, the data that we got given is actually we know the rate law is going to equal to rate constant K times A to the first power and B to the first power. Right. So now we actually start to guess. Okay, you can give me a guess. Step 1, step 2, or step 3. Okay. So let's say we start from step 2. Okay, so we guess step 2 is the rate limiting step. Okay. Then we can see this. Step 2 is this, right? Step 2, you see this x plus c that give you y. Therefore, the rate law is going to be equal to a random constant k times X times C.
Okay, you can only do this when you have elementary step. Okay.
If today you have 2x plus C give you 3y,
How do you write your red law?
R is going to equals to rate constant K times x to the second power times C to the first power.
Okay, and again, you can only do this if you have a elementary step. Okay.
All right, so this actually we're going to get started with. Then you start to compare this one to that one.
Do they look alike? Do they look the same? They are not, right?
Because the inventory code is actually want to actually write the rate equals rate constant K times your reactance. Here your X is not a reactant, your C is not a reactant, right? So you know they don't look the same. So you need to actually do the substitutions. Okay. You will need to actually use the equilibrium constant K to substitute those non-reactant species. Okay, so how do we actually do the substitutions? Let's look at X, right? So you start from step 2. Okay, I want to actually somehow substitute the X. Okay, you need to actually go to the other equations, meaning you either go to equation 1 or equation 2 to find out how you can just substitute your X, right?
So if you look at equation 1 and 2, which one has X? Equation number 1, right?
So then you can write this, right? KEQ1 is equals to X over A times B. Therefore, you know the X can be expressed as KEQ1 times A times B.
Okay.
And that's what you're going to do. Okay, so here you know you can rewrite this, right? It's K times KEQ1 times A times B, right? But here, that's actually this part, right? So that's actually what you get in times C.
Okay.
So I guess this rate constant here, I want to put rate K2 because it's actually coming from the elementary step 2. Okay. And once you have this, then you should know that this is a constant, that is a constant. So they can combine to become a new constant. Okay, so I use that as, let's say, K final.
Okay, it's actually the final rate constant after this derivation, right?
Then it's going to equals to A times B times C. So that's actually the new red law you can actually derive, right?
So if you look at this, what you have, the structural data is actually the reaction rate is going to equal to a rate constant K, and now we call Kf, right? Times A to the first power, B to the first power, times C. Okay, so if you look at these equations, you realize that every single species in this equation, they are all reactants, right? So actually, you already come to the status that you want. You want to actually express the rate using the concentration of reactant. Okay, so this is actually, if you assume that step number 2 is actually related to step, this is actually what you get. Okay, then you need to actually compare like this one to the experimentally determined red law. Okay, and check are they the same or not. Okay, so what is actually the experimentally determined red law? That is actually the one that was provided inside the questions, right?
it tells the reaction rate is going to equal to reaction K as A to the first power, B to the first power, C to the zeroth power. Okay. That means if you actually assuming your step number 2 is actually a relative step, the rate law you got doesn't agree with the experiment in 1. Right? Therefore, you know what? Therefore, step 2 is not your rate limiting steps. Okay, so you know step 2 is not the things you are looking for. Then you do another guess. Okay, so let's say we guess step 1 is the rate limiting step. Okay, so the step 1 is what? A plus B, they give you X. Right? So let's actually step number 1. Okay. So once you see this, then you can try to write out your rate law is going to equals to the constant K times A times B. Okay, so that will be actually the rate law because soon step 1 is actually a relative step. Okay. And then check this. Is A your reactant? Yes. Is B your reactant? Yes. Right? So you're done. So if you step number 1 is actually your rate law, then this is actually what you're going to write. Okay. Then you compare that to the experimentally determined one. Then you realize that they do agree with each other. Right. Therefore, you can actually conclude that the step 1 is the rate limiting step. Okay. Therefore, you know the answer will be just 1, right? That's step number 1. Okay, so this is actually how you figure out what are the rate limiting steps. This is actually how scientists figure out what the reaction, what the possible reaction mechanism is. Okay? So any questions so far for the concept we just went through? Okay, so let's recap the things that we learned. Okay. So every time you see a question like this, okay, the typical feature you're going to see is that you're going to see a multiple step mechanism. Right, and those steps we call it elementary steps, which you can write out the result directly based on the equation you are given. Okay, so inside the equations, okay, it will must provide you with the experimentally determined result, right? So you should know what that reaction is. Okay, and then you start to guess which elementary step you think is actually the relevant step, and write out your corresponding result, and check all the things you write out based on your elementary step. Are they your reactants? If they are not, then use the equilibrium constant to substitute those species. Okay, until you can write your result in terms of all the reactants. Okay, and once you reach these stations, compare that to your experimentally determined result. Okay. If they are not the same, then your assumption is wrong. Go to the next step. Okay. If they actually correct, if they actually agree with your experimentally determined result, then that specific step will be your rate limiting step. Okay. And then if they are the relative step, okay, typically when you write out the elementary step, you'll put this. Okay, you'll say, okay, this is actually the slow step. Okay, and all the others will be the fast step. Okay, so this will be fast. This will be fast. Okay. So that's pretty much the core concept for the reaction mechanism. Okay. Any questions so far? Yes.
The answer is A because if you assume A is your rate limiting step, okay, then the rate law you write out based on your elementary step, it agrees with the experimental determined rate law. Okay, and in this case, it just happened to be one of the elementary steps. It directly have A and B, right? So you can check this very easily. Yeah, so because that's actually the limiting step and also the elementary step, you can write out the rate law. You already have A and B directly, right? So once you get familiar with this concept, okay, I guess everybody now has the ability now. If you look at equations, right? You know the second one will be x to the first power and c to the first power for the rate law, right? And the very last one will be y to the first power. Okay, so you can easily see that already. Okay, so you know, okay, what you're looking for is actually if I write out this, we actually agree. Some of the question is very simple, but this one is actually very simple, right? Because C, A, and B directly in your step number one. So you can just look at, okay, this is going to be first part of A, first part of B, and A and B is actually my rate and agree with my experimental rate law described in the question. That you know step number one is actually the answer, right? So I intentionally start with step number two, because that's actually how I can tell you step number two, it is not. So that you will see why step number one is actually an easy answer to choose. Does that make sense to you now? Okay, cool. All right, so with this in mind, let's do a few more practice. And then you'll realize that once you get the ideas, it's actually really, really simple. Okay, so it says for the reaction NO2 plus CO, like give you NO plus CO2, at temperature below 500 K, the rate law is rate equals rate constant K times NO2 to the seconds power. And then they propose two different mechanisms, and actually which one is the correct one. Okay, so I guess Q is actually very simple, right? Which mechanism is actually correct? Okay, either one or two, right? The data that you have, that is actually data that you have, right? The experimentally determined rate law is rate equals to rate constant K times NO2 to the seconds power. Okay. Then plan. Right. So in the if you look at the mechanism one and mechanism two, what's the big difference between mechanism one and two? Do they have the same elementary steps? If you compare the mechanism one and mechanism two, right? They all propose two steps, right? Are those two steps the same or different? They're the same, right? What's the differences between the two? The only difference is actually when they write the slow step. The mechanism one consider the first step is slow, right? The mechanism two consider the second step is slow. Right. So right now it's actually that's just okay. We think that's actually the mechanism we're going to go through, but I'm not sure which one is actually the slow step. Because the slow step will be your rate limited step, right? So you should write your rate law based on the slowest one. Okay. Then okay, so now we just need to see, okay, what are the rate laws that we can derive based on the slow step, right? So if you do the mechanism one, you know the slow step is actually the first step, right? Then you can write out your rate law is going to equal to rate constant K times NO2 to the seconds power, right? Everybody have a problem with this? When I write out this from the slow step of mechanism one.
Everybody is fine with this? Yes.
How do I form the equation? You mean the mechanism 1, mechanism 2? R equals K times NO2 squared. Okay. So this is actually the things you can only do it from the elementary step, right? You write out based on this equation. Right, so what you really do is actually the rate is going to equal to rate constant K times reactant. Okay, so the reactant you have is actually NO2 times NO2, right? Because those are the reactant that you have. Okay, so NO2 times NO2 is concentration to the second power. Is that correct? Yeah, good. Okay, so once you get to this, you need to compare to your experimental one, right? And then you check, are they the same or different? So are they the same? They are, right? And that's the end of the story. If they are the same, they're done. That's the answer. Okay? So let's say, okay, you're not very lucky, right? You assume the mechanism 2. If let's say just start with mechanism 2 for no reason. Okay. So the mechanism 2, you know the rate is going to equals to, then this will be actually the things you need to actually work with to start with, right? So the rate is going to equal rate constant K times CO times MO3, right? So starting from here, you realize that CO is actually your reactant, right? Is NO3 your reactant? Is NO3 your reactant? What is NO3? Intermediate, right? So you know this cannot be written. This is actually not, you are not done yet, right? You need to actually substitute your NO3. Okay, so how do you substitute NO3? To go to this equation, write out that KEQ is going to equals to NO3 times NO divided by NO2 squared. Therefore, you can write that NO3 is going to equals to KEQ times NO2 squared divided by NO, right? Then you put it back to here. Okay, so after you do this, then you know your rate is going to equal to rate constant K times KEQ times CO times NO2 squared divided by your NO. Okay, and up to this point, then you check what you have. You have your CO, right? Is CO your reactant? It is, right? Is NO2 your reactant? It is, right? Is NO your reactant? It is not, right? That's your product. Okay, so what does this mean? This means after all this work, you come to equations, you still have that product term inside your results. Okay, so that's not the final form that your question have. Therefore, you know this one cannot be your answer either. Not either. This one cannot be your answer. Okay, therefore, you know mechanism 1 will be the correct mechanism. All right. So we say so much things about this reaction mechanism, right? But when you handle these things, you also have to pick the one. And very likely that's actually the easy answer you can pick. Okay, that if you see the elementary step, it can quickly give you first, okay, you will have this property, okay, it's going to see as many reactants as possible. Right, because if you look at this quotients, right, and the previous question the same. You see actually reactants directly already, right? So you could actually only do 0 or 1 or 2 operation, you can get back to the red law. They can express in terms of the reactant only. Okay, so those are the things that you should have in mind. Okay, but this is actually how you solve these type of questions. Okay. Next one is actually interesting. Okay. So scientists propose this. Okay, for these reactions, ClO minus plus I minus give you IO minus plus Cl minus. Okay, they propose this 3 elementary step. The first step is fast, second step is fast, the third step is slow. Okay, so if they want actually to derive the red law of this mechanism. Okay, so we're just going to do the same thing. Okay, so first thing first. Okay, what are the reactions? And I minus, right? So those are the things you want to have your final expressions contains these two. Okay. And then you know there are actually 3 elementary steps, right? So which one should you actually pick to start with? The one with what? The one with slow, right? That's actually a rare limiting step. Okay. So questions. It's actually you want to derive the red law, right? Data. Okay. You start. You have this is actually your data. So plan. Start with slowest step. Okay, therefore you know the rate can be written as rate constant K. Okay, let's call it K3 because start from state number 3. Okay, times OH minus times HIO. Okay, so that's where we get started. Okay, so once you write this out and you start to check, is the things I have, are they actually reacting? Right? So that's why you have to go back to check this. Okay, I guess let's write this. Okay, reactants. You're going to have ClO minus and the I minus, right? I realize that the things you have now are tensional reactant. Therefore, you just start to substitute these non-reactants and then to hope that you can actually make it all become reactants, right? So let's look at for the OH minus. So to do that, then you're actually going to the other 2 equations and looking for the OH minus. Then realize that equation number 1, the equation that contains OH minus, right? So you actually go back to equation number 1. We want to do the OH minus. Therefore, we go to step 1. Therefore, we can write out the KEQ. It's going to equals to HClO times OH minus divided by ClO minus. Is that a KEQ? Do I missing anything? Water, right? Should you put water inside the KEQ? No, okay, let's actually a rule for the writing the equilibrium constant, right? Pure solid, pure liquid, they don't go into your KEQ. Okay, so make sure you know this. Okay, so you should actually write, you shouldn't write the water into your equilibrium constant. Okay? So that is actually a KEQ that you should actually have, right? Therefore, you can rearrange this to write out your OH minus can be expressed as constant K. Let's say KEQ1 times ClO minus divided by HClO.
Okay. So that's actually how you can actually express your OH minus from your equation number 1. Okay, then you can actually work on the other species, which is your HIO, right? So you're looking for HIO, then you realize that here is your HIO, right? So introduce step 2, write your KEQ2. Therefore, you can write HIO times Cl minus divided by I minus times your HClO. Then you can actually reorganize this to figure out what's your HIO looks like, right? So HIO can be equals to KEQ2 times I minus times HClO divided by your Cl minus. So that's the best you can do, right? Then the next step is actually you plug this back in to here and to here. Therefore, you can write your red law is equal to K3 times KEQ1 times ClO minus divided by HClO. HIO will be KEQ2 times I minus times HClO divided by Cl minus. Okay, so I just put all the constants to the front. Okay, because those constants eventually will be combined. Then this I can write as a K final, right? The final rate constant. Okay. So these 3 will give you the final rate constants. And then you'll realize that this and that will cancel out, right? So you're going to have ClO minus times I minus divided by Cl minus. Okay, so this will be the rate law you can actually derive following all the things. Okay, so when you come to this step, you pretty much do everything you can, right? And then you start to check. Is this your reactant? It is your reactant, right? Is this your reactant? Okay, just so reactant is this and that, right? ClO minus and I minus. So you can see the things on your numerators. They are your reactants, right? How about Cl minus? It is not, right? But this is actually all the things you can do. Okay, so what does this mean? This means the proposed mechanism, they are not the correct one. Okay, so let me say actually, the scientists when they propose these things, right? So you do everything you can. Then you end up with something that still have your product inside, and that's just not right. Okay, so this actually tells you that these mechanisms still have some problems. So what scientists need to do is what? Go back and repropose something. Okay, then find out what could be a reasonable mechanism to explain the things we see. Okay, so again, this is actually just part of the life that scientists can go through. Okay, let you mention they have the perfect mechanism, but after they do all these translations, they realize, let's see, that's actually a product. In fact, I know that lost. Well, I screwed it up, then I will start again. Okay, so this is actually just examples I want to demonstrate the concept. Okay, the other thing I want to emphasize in this example is that you see how actually to substitute those non-reactant species using other elementary steps, right? Those are the things you have to get very good at. Okay, because some students will get confused when they start to substitute the species. Okay. Very last thing I want to actually talk about in this equation is that, okay, I want you to actually look at this. So right now, I guess we have no problem to identify that the reactants in this reaction is what? ClO minus and I minus, right? Product. IO minus, Cl minus. Okay. So I think most people won't have problem with this too, right? Because you know the things got cancel out, right? So this will cancel with that. This will cancel with that. This will cancel with that, right? And this will cancel with this. Therefore, reactant is this, product of this, right? So it's very simple. Yeah. Now, the things that students may get confused is if I ask you what are the intermediate, so what are the intermediates? What are the intermediates? HClO, OH minus, HIO, anything else? Is H2O intermediate? How do you know H2O it is or it is not? So what is intermediate? Yes, intermediate has a very important properties that it must be produced. That means when it first showed up, it must show up on the product side. Okay, so the things that doesn't actually show up on the product side in the beginning, they will be your catalyst. Okay, so let's actually biggest differences. Okay, so the catalyst will be your H2O. Okay, so this is actually very important because you are going to encounter some question like this. Okay, I give you multiple elementary step. I want to ask you, okay, what is actually H2O? Then you need to be able to answer that it's the catalyst, not the intermediate. Okay, and then everything you cross out, that first show on the product side, they will be your intermediate. Okay, so reactant, product, intermediate, catalyst. Okay, these are the four species that you wanted to be able to recognize from the elementary steps. Okay. Because it first shows up on the reactant side, H2O, right? Intermediate will show up on the product side because it was produced. So let's say the HClO was actually shown up in the first step on the products. So all three steps, okay, that sequence, right? Step number one, step number two, step number three, is actually step number one happen first, and all the way to step number three. Okay. So those are the key information that you need to actually memorize. Okay. So I guess I need to. Okay, so the very last things I want to go through today is this. Okay, Arrhenius equation. But before we go into all these things, there's actually one very important figure they need to actually recognize. So these are actually the things I mentioned in the beginning of the class, right? So when we have the reaction coordinates, you always start from the reactant. And then you end up with the product. Okay? So along the way, you may actually have these things. Okay, let's say these are the stepping. Let's say this is actually the steps you have to go through. Okay. So the first thing you should know, if you see a figure like this, is that the product is actually higher energy than the reactant, right? So if this reaction happens, it will be a endothermic reactions, right? You have to put in the energies so that these things can happen, right? So the energy difference between your reactant and product, this is the things that you're actually familiar with. That's your delta H. Okay, so energy difference between your reactant and product is the delta H, the change of enthalpy. Okay. You see this curve, right? Which one has the highest energy? This, right? This to left is what? It's the activation energy. It's the barrier. It's the main barrier. They come through. Okay. And if you look at these reactions, you should see that this guy, these little values here, those are your intermediate. Okay, so you know this. Okay, you'll be testing all this concept. Okay, so this value is called the intermediate. Okay, how about this? Very good. Okay, this is called the transition states. Okay, so this lead and lead is the transition state. Okay, this is all very important. This is to understand these pictures. Okay, that's actually very valuable. Okay, so tell me now, then, how many transition states for this specific reaction? How many? Three. Okay, how many intermediates? Two. Okay, so everything is these transition steps, right? That is actually the mechanism, that elementary step 1, 2, and 3. Okay, so you see this first hump, you go from your reactant to an intermediate. That first hump is actually the elementary step 1, right? And then from the first intermediate to the second intermediate, you see another hump. That's your elementary step 2. And there's actually another one that goes to your product. That's your elementary step 3, right? So you have step 1, 2, and 3. Okay, everybody follow this? Now I'm going to ask you a question. Yes. Okay. How do I know it is? Because the product has higher energy than your reactant, right? Yeah, the way you can make your product has the same symmetrical to your product, then you have to provide energy to make it happen. Yeah, so that's why it's actually absorb heat. That's why it's actually absorb. So the question I want to ask you is actually the step, which step is actually a relative step? Step number 2. Okay, it's very important. Okay, and then how do you calculate En is actually the peak of this energy to your reactant energy. Okay, those are very important information that you can actually understand. Okay, so the final equations they want to go through for today Give me 3 more minutes. Let me finish this. We'll do the question in the next lecture. Okay. But this is actually a quick summary. Okay. The rate constant K is going to equals to this so-called frequency factor. Okay, times exponential terms. Where inside the exponential term you have your activation energy EA divided by the constant R and the temperature T. Okay. So these two equations, they are actually the same. The only difference is that I have natural log on both ends. Okay. But that's actually the final equation that you're going to get if you take the natural log. Okay. This equation is the things that you got tested the most. Okay. It basically says how the rate constant K is going to change with the temperature. So if you look at this, you have two rate constants, K1 and K2. Okay, there are two temperatures, T1 and T2. Okay, and there's actually another term, is actually your EA, right? So in your homework quiz and midterms, you are going to see, if you see a portion contains two rate constants, two temperatures. Okay, that's the key word for this specific equation. That's the go-to equation. Okay, so all I want to do is actually ask you the 5 variable here, right? K1, K2, E1, T2, and EA. It's going to give you 4 out of 5 to calculate the one that completed. Okay, so that's the concept of this simple equation. Okay, so very last thing, the catalyst. Okay. So the catalyst doesn't change anything. The only thing it changes, it doesn't change your equilibrium, okay? The only thing it changes is this plot. Okay, it's going to lower down your EA. So this is actually without catalyst, right? But with catalyst, it may become something like this. So the energy of your activation energy can be greatly reduced by the catalyst. Okay, that's the only thing we do. But the catalyst doesn't change anything else. Okay, the only thing it changes is activation energy. And the reason I emphasize this is because your homework, your quiz, is going to give you all the options. Okay, but every time you see the catalyst, only look for EA, nothing else. Okay, so that's actually a very important concept. Okay, I'm sorry I'm a little late. Okay, but that's it for today. Thank you.